Space is vast and full of wonders. It's a realm of infinite possibilities, where the laws of physics as we know them are constantly being tested and sometimes even broken. Among the myriad of celestial phenomena, black holes stand out as some of the most intriguing and enigmatic objects in the universe. One of the most mysterious objects is a black hole. These cosmic enigmas have fascinated scientists and astronomers for decades, pushing the boundaries of our understanding of the universe. Imagine a place where gravity is so strong that nothing, not even light, can escape. That's a black hole. These regions of spacetime exhibit such strong gravitational effects that they warp the very fabric of the cosmos around them. They are like cosmic vacuum cleaners, but on a much grander scale. Black holes can pull in matter from their surroundings, including stars, gas, and even entire solar systems, with their immense gravitational pull. Black holes are incredibly dense. They are formed when massive stars collapse under their own gravity at the end of their life cycles, compressing their mass into an infinitely small point known as a singularity. They pack a huge amount of mass into a tiny space. This immense concentration of mass distorts space-time to such an extent that it creates a region from which nothing can escape, not even light. This makes their gravity incredibly intense. The closer you get to a black hole, the stronger the gravitational pull becomes, creating a point of no return known as the event horizon. Think of a bowling ball on a trampoline. The bowling ball creates a dip in the trampoline just as a massive object creates a dip in the fabric of space-time. It creates a dip, right? That's like gravity. The more massive the object, the deeper the dip. This analogy helps us visualize how black holes warp space-time. Now imagine squeezing that bowling ball into something smaller than a pinhead. The dip would become incredibly deep, representing the intense gravitational pull of a black hole. The dip would be so deep that nothing could escape. This is why black holes are such powerful gravitational forces in the universe. Black holes are invisible to our telescopes. Because they do not emit light, they cannot be seen directly. Instead, we infer their presence through their effects on nearby objects. We can't see them directly because light can't escape their pull. This makes them one of the most challenging objects to study in the cosmos. However, we can detect their presence by observing how they affect nearby stars and gas. The gravitational influence of a black hole can cause stars to orbit around an invisible point or gas clouds to swirl in a distinctive pattern, revealing the hidden presence of these cosmic giants. Stars like our sun are giant balls of hot gas. They are the fundamental building blocks of galaxies, illuminating the cosmos with their radiant light and providing the energy necessary for life as we know it. They are born in nebulas, which are clouds of gas and dust. These nebulas are often referred to as stellar nurseries because they are the birthplaces of stars. Within these vast clouds, regions of higher density begin to form. Over millions of years, gravity pulls this material together. As the gas and dust condense, they form a protostar, which is the earliest stage in a star's life cycle. The process is slow and gradual, but the force of gravity is relentless. The core gets denser and hotter. As the temperature rises, the pressure in the core increases, leading to the conditions necessary for nuclear fusion to begin. This is a critical phase in the life of a star. Eventually, nuclear fusion begins, and a star is born. This fusion process converts hydrogen into helium, releasing a tremendous amount of energy in the form of light and heat. Stars spend most of their lives fusing hydrogen into helium. This phase, known as the main sequence, can last for billions of years. During this time, the star remains relatively stable, shining brightly in the night sky. This process releases enormous amounts of energy, which makes the star shine. The energy produced in the core radiates outward, reaching the star's surface and then traveling across the vast distances of space. The sun is about halfway through its life. It has been shining for about 4.6 billion years and is expected to continue for another 5 billion years. During this time, it will continue to provide the energy that sustains life on Earth. What happens when a star runs out of fuel? As a star exhausts its hydrogen supply, it undergoes significant changes. The core contracts and heats up, while the outer layers expand and cool, leading to the next stage in the star's life cycle. It depends on its mass. The fate of a star is determined by its initial mass, which dictates how it will evolve and eventually die. Massive stars have a different life cycle compared to smaller stars. Smaller stars like our Sun will expand into red giants and then gently shed their outer layers, becoming white dwarfs. This process is relatively gentle compared to the dramatic end of more massive stars. These are like dying embers, slowly cooling down over billions of years. White dwarfs no longer undergo fusion and gradually fade away, leaving behind a remnant that tells the story of a star's life. Massive stars much larger than our Sun have a more dramatic fate. These colossal giants, often tens or even hundreds of times the mass of our Sun, live fast and die young in the grand scheme of the universe. Their life cycles are intense, burning through their nuclear fuel at a staggering rate. When they run out of fuel, their core collapses under its own gravity. This process is inevitable and marks the beginning of the end for these massive stars. The core, no longer supported by the outward pressure of nuclear fusion, succumbs to the relentless pull of gravity. This collapse happens in a fraction of a second. In this incredibly brief moment, the core's density increases dramatically, and temperatures soar to unimaginable levels. The speed and violence of this collapse are almost beyond comprehension. Imagine a skyscraper suddenly imploding in on itself. The structure, once towering and majestic, crumbles inward in a catastrophic failure. This analogy helps us grasp the sheer scale and suddenness of a star's core collapse. The collapse is so violent that it creates a shock wave, which blasts the outer layers of the star into space. This explosive event is known as a supernova, and it releases an enormous amount of energy, outshining entire galaxies for a brief period. This is a supernova, one of the most brilliant events in the cosmos. The light from a supernova can travel across the universe, reaching us millions of years after the event itself. It's a spectacular finale to the life of a massive star. The core, however, continues to collapse. Even after the outer layers have been expelled, the core's fate is sealed. It keeps contracting, growing denser and hotter with each passing moment. Gravity keeps pulling everything inward. The force of gravity becomes so intense that not even light can escape its grasp. This relentless, inward pull is what drives the core to its ultimate destiny. If the core is massive enough, nothing can stop its collapse. The core's mass determines its final outcome, and for the most massive stars, this means an unstoppable journey towards infinite density. It shrinks until it becomes infinitely dense, forming a black hole. This is the ultimate end for the most massive stars, a point where the laws of physics as we know them cease to apply. The black hole, with its immense gravitational pull, becomes a mysterious and fascinating object in the universe. Imagine approaching a black hole. As you get closer, the pull of gravity gets stronger and stronger. Eventually you reach a point where not even light can escape. This boundary is called the event horizon. Think of the event horizon as a one-way membrane. Once you cross it, there's no going back. You would be trapped forever, pulled towards the singularity at the center. The event horizon is not a physical surface, it's just a region in space where gravity becomes inescapable. It's like falling into a waterfall. Once you go over the edge, you're not climbing back up. Singularities, where physics breaks down. At the very center of a black hole lies a point called the singularity. This is where all the matter in the black hole is concentrated. It's a point of infinite density and zero volume. Our current understanding of physics breaks down at the singularity. We don't have the tools to describe what happens there. It's like trying to divide by zero. Our equations just don't work. Imagine trying to squeeze all the information in a library into a single point. That's the kind of mind-boggling concept we're dealing with when we talk about singularities. Types of black holes. There are different types of black holes classified by their size and mass. Stellar mass black holes form from the collapse of massive stars. These are the most common type. Supermassive black holes are millions or even billions of times more massive than our Sun. They reside at the centers of galaxies, including our own Milky Way. How these behemoths form is still a mystery. We know they play a crucial role in the evolution of galaxies, but their origin remains an active area of research. Black holes aren't cosmic vacuum cleaners. Despite their reputation, black holes don't suck everything in like cosmic vacuum cleaners. They have a gravitational pull, just like any other object in space. If our Sun were replaced by a black hole of the same mass, Earth's orbit wouldn't change. We would continue to orbit the black hole, just as we orbit the Sun. It would be dark and cold, of course, but our planet's motion wouldn't be affected. black holes only become dangerous if you get too close to them, crossing the event horizon. Keep your distance and you'll be fine. Unraveling the mysteries of the universe. Black holes are more than just fascinating objects, they are cosmic laboratories that allow us to test our understanding of gravity and the nature of space-time. Einstein's theory of general relativity predicted the existence of black holes. Observing them provides evidence to support this theory, showing that it accurately describes the universe on a grand scale. By studying black holes, we gain insights into the fundamental laws of physics and the workings of the cosmos. They are windows into the most extreme environments in the universe. Conclusion: Guardians of the Cosmic Order. Black holes, once considered mere theoretical curiosities, are now recognized as integral parts of the cosmic tapestry. They are both awe-inspiring and somewhat terrifying, a testament to the immense power of nature. These enigmatic objects continue to fascinate and challenge our understanding of the universe. As we delve deeper into their mysteries, we uncover more about the fundamental forces that govern the cosmos and our place within it. Black holes are not merely cosmic abysses, but rather guardians of the cosmic order, shaping the evolution of galaxies and reminding us of the boundless wonders that lie hidden in the depths of space.